In this two-part talk, we're going to have an introductory look at data types within C++. And in this, the first part is really just going to be introducing what primitive types of data C++ supports. So primitive data, I'm taking it for granted that you're all aware of what primitive data is, compared to either more complex data types, things like classes or compound data structures where things are combined together. So by primitive data, we mean very simple, elementary forms of data that can't be broken up, chopped into smaller component parts. Actually, taking a step back, and it is actually useful to think about this generically. When we talk about different types of data, if we were to ask a more fundamental question, what is a data type? Data type we can define as comprising two different parts to it. If we want to specify a data type, what we need to have available is a list of valid values, if you like, instances of a valid instance of a particular type of data. And normally alongside that, we also define a set of operations, things like addition, multiplication, or whatever, that we can meaningfully apply to that data or to instances of that data. So values alongside operations, and both of them combined provide us with the notion of a data type. C++, same with lots of other languages, when they're classifying data, we either sort of talk about primitive data types or class or compound or structural data types as well. For the primitive data types, these are all the built-in ones, they will come with a list of predefined or a way of identifying what represents the correct value, and also a list of supported operations. You can compare and contrast this with a class data type, where we as the programmer, we get to define what constitutes a valid set of values for that instance, and we also get to decide or to publish what public methods are available for that data type. Within C++, there basically are two different types of primitive data, and they're both types of numerical data. Now, at this point you might be thinking, okay, here we can see we've got integers and we've got floating point numbers. What about Boolean variables? What about characters, chars, things like that? Actually, we'll see those in a second. In C++, they're classified as integers, or they're bundled under integer data types. And that's going to have some important things that we need to consider. But at this high level, C++, we need to understand then that if we're talking about primitive data, either we're talking about integer data types or floating point data types. And you can see down at the bottom of this that both data types, there's a wide range of operators, operations that can be applied to them. And in quite a lot of cases, there's corresponding operations. We can add two integers. We can, as I say, we can do it for two floating point numbers. But there are some variations, because integer data types basically are stored as just an ordinary binary number, and that opens up some form of bit manipulation that we can't so easily apply to floating point representation. So we'll start off having a look at the integer data types that we have defined or available to us within C++. There is actually 9 of them. You maybe think, oh, that's a bit more than I was expecting. Within languages like Java or C#, well, an int is really what we use. Might use a long, but that's about it. In C++, we have a char, a character, a short int, an int, a long int, an unsigned char, an unsigned short int, an unsigned long, an unsigned long int, and a bool. Indeed, we also have a bit more than this. We have sort of long longs and other things related to that as well. Most common, three most common types are int, char, and bool. Now, for Boolean variable, they're all classified as integer data types, not really gets under the surface as to how they are stored and represented within memory. So obviously an integer gets to be stored as just an ordinary binary number. Characters will have ASCII or Unicode equivalent numbers. Again, that's just a number. And a Boolean value, we can think of it again as a 1 or a 0. Again, just a number. So chars and bools, they can be, in fact they are represented under the surface. They're stored as numbers. For the other ones like unsigned, short int, or just a long int or things like that, they just, again, they're basically numbers. How they differ fundamentally is in the amount of storage, amount of memory that they set aside for holding themselves, which will determine the biggest and the smallest number that we can put within them. So ints, most common type. They're whole numbers, no decimal point. At the minute within C++ in most platforms, if you talk about an int, you're mostly talking about a 32-bit integer value. So if it's a signed one, you have roughly minus 2 billion to positive 2 billion as the range of permitted values. And this maps on well to ints as are declared within, say, Java and C#. Now, I say at the moment, for example, whenever I first learned C++ some time ago when I was at doing A-levels at school, ints were at that point 16-bit by default on most platforms. So C++ doesn't have a one defined size for an int. It is allowed to vary and change between platforms, and it's something that has slowly varied over time. And I suppose in the fullness of time, it's maybe reasonable to expect ints to default to 64-bit values whenever there's a need for that to be the case. For chars then, single characters, if they are represented using ASCII, then they're 8-bit values. For Unicode, generally 16-bit values, though Unicode also has an 8-bit character set that maps onto ASCII as well. And obviously for Boolean, we need a single bit, a 1 or a 0. You might have noticed when I was showing the list of operators back a few slides that there was a size-off operator that's available. It can be applied to any floating point or any integer data type, and it tells you the number of bytes that are used to hold that value in memory. And what I just said in the last slide, that C++ doesn't make any assumptions, doesn't say that an integer must be 4 bytes in size, unlike, for example, Java and C#, where they have defined the size of the primitive data types. In C++, you can assume if you want to. It is slightly dangerous doing that. If you do want to be precise, you can use the size-off operator just to check how many bytes are indeed used for holding the different data types. You can see a couple of examples here, one where we ask the size of a data type, an int itself, the other one where we ask the size of a variable. Again, that will be based on the type and how many bytes it is using. There's a limits file within C++, and this file, other than using the size of, use size-off to work out the number of bytes, and then from that you could then work out, okay, how big or small it can be. You need to understand though if it's signed or unsigned. So the limits file tells you, or defines within that, what is the largest and the smallest value for each of the different primitive types. C-limits is the one we have here, and you'll remember from one of the previous talks that C-limits then is the C++ version of the original C or limits.c file. So within this here, we will define, you can see some of the values down here, the maximum signed character value, 127, the maximum unsigned character value, 255. So obviously if it's unsigned, then we're not using any negative values. And there's a progression as we go down through the table. It's worthwhile having a look at this progression because mostly it makes sense until we get to the bottom and then it falls apart. So chars, they are 8-bit values. That's okay. Shorts are 16-bit values. Again, that's perfectly sensible. Ints are 32-bit values, and again, that all makes good sense. Now, along then, if you're coming from Java or C#, along is an extra big integer value. Normally it's 64 bits in size. And you might think, okay, C++, it supports along as well. Surely it's going to be 64 bits in size. It isn't. Well, it depends on the platform, but if you are, for example, using Visual Studio, then along at the minute is 32 bits in size. It's the same size as an integer. And if you do want a 64-bit integer value, if you're using Visual Studio and C++, at the minute you have to use a long. So it's not only a long, but it's an extra long. It's confusing, it doesn't make any sense, it's per design, but that's just the way it is. It's mentioned signed and unsigned. Okay, if it's signed, you can have negative and positive values. If it's unsigned, it's always going to be positive, but you've got a longer or a bigger positive range of values. Why do we have them? Historically, it made more sense. Nowadays, if you've got an integer, say 30-bit, minus 2 billion to positive 2 billion, there's not maybe that many applications where you're interested in the 0 up to 4 billion. I say that if you're doing a 30-bit operating system, it does make a difference if the biggest size you can support is sort of 2 gigs of RAM as opposed to 4 gigs of RAM. So there, whether or not it's signed does have an impact. Going back further into the past, let's say where ints were 16-bit in size, then depending on the mathematical operators you were doing, sometimes you would exceed 32,000 and you might want to go up to 64,000. So having things being signed or unsigned probably have more of an impact than they had nowadays. Certainly in the past, quite often it was a distinction that needed to be made. Next up is floating point data types. And there's 3 different types supported within C++: float, double, and long double. Again, the only way that they differ is in the amount of memory that is set aside for storing them. And you'll see in the next slide that if you were sort of thinking back to our ints, where we had a short, an int, a long int, or sorry, a long and a long, we'll have a look in the next slide as to if we or not we've got the same confusing situation here. Doubles, they typically use twice the amount of memory of a float, and that gives rise to some of the terminology. You might see or hear use of a single precision number. Single precision is generally a float. A double precision is twice the precision of a single floating point number. So you got a float and a double because it's worth roughly double the amount of precision is available within it. Just to be slightly confusing and to be slightly inconsistent with the other one, so float is a 32-bit value, that's fine, it maps on well to Java or C#. Double and long double, they are both 64 bits in size. So again, 64-bit double maps on well into Java and C#. So in this sense, floats and doubles have good correspondence with Java and C#. Going for most compilers at the minute in terms of how they define it. For the data types, if you're specifying literal values, just a floating point number, you can see what you need to add on to it if you want to be explicit in terms of the type of data that you're specifying. So if it's just an ordinary number, 3.14, then by default that is assumed to be a double. If you add on an F, lower uppercase, to the end of it, then when the lexical analysis, the parser's looking at this here, going through and taking out this as a token, it will say it will consider it to be of type float. And if you put in an L, which is pointless at the minute, given the same resolution as a double, that will then be treated as a long double. So takeaways on this, C++ gives you a decent number of primitive data types, much the same as Java and C#. There's a little bit more flexibility in C++. That said, nowadays you generally only use a small subset of the available different data types, and the other types have become somewhat less relevant over the years.